and then as long as you want today and as long as you want tomorrow, I'll answer homework questions. Other than that, I can just, make up some questions related to the test and stuff, and we can go through that. So we're not going to do anything new until after the test. Okay, so exam 4 is on Wednesday. And the topics are going to be everything up through energy. And for today and Tuesday, I'm still going to assign the repeated problems, but I'm not going to give anything new. So you've already done all the problems that, they've already all been assigned before. And before we start getting into questions and problems and stuff, let me just give what I think of as kind of like the basic structure of this section. So first of all, in a way, you can think of potential energy as kind of, I think, the key concept in all of this. Because you can use potential energy to calculate a couple of different things, go in very different directions of what you calculate. So first of all, potential energy is useful in kinetics problems for figuring out, so you can use it for conservation of mechanical energy. You can also use it for the more general form of that, the work energy principle. And so I'll talk about how to fit it into both of those. And then here are the two calculations you can do with potential energy, not related to body kinetics, but just if you're asked for different quantities. One of them is you can calculate the force vector produced by that force field as the negative partial derivative of the potential energy with respect to x, that's the x component, and the negative partial derivative of the potential energy with respect to y, that's the y component of the position. And this force vector always points toward the steepest decrease in potential energy. Okay, so when you have a force field, in other words, a conservative force, you have a force that only depends on the object's location. Wherever the object is, that force is pointing towards the direction the object has to go for the greatest decrease in potential energy. You can think of it as like the force is always trying to decrease the potential energy as quickly as it can. Okay. So if you think of it as gravity as an example, gravity is always the easiest example to use when you're trying to make sense out of stuff. So gravity is a force field or a conservative force. If you know the location of the object, you know the force vector that it applies. In fact, you don't even have to know the location, but that doesn't matter right now. And so say the object goes through its path and ends up here. Okay. The potential energy is the mass times 9.81 times the height. Okay. The negative derivative of that with respect to y is negative mg in the y direction, so that gives you the force straight down. And the force vector straight down points in the direction that the object has to move to decrease potential energy the fastest. There are ways you can decrease the potential energy. If you move the object this way, it decreases. This way, it decreases. But the fastest way to decrease the potential energy is straight down. And so that's the direction that the force points. Okay. And then the second type of calculation that you can do is the work done by the force is equal to the negative change in potential energy. So if you calculate the potential energy at instant 1 and the potential energy at instant 2, take the difference at 2 minus 1, that gives you the change in potential energy. Multiply that by negative 1, and that gives you the work that that conservative force has done from instant 1 to instant 2. So these are kind of the important things to keep in mind that you can calculate directly from the potential energy. If you're doing kinetics, the main reason you would want to use this is if not all of your work is done by conservative forces, then you have to use the work energy principle. And this is how you get potential energy into the work energy principle. So for kinetics, using energy, if all the work on an object is done in force fields, in other words, it's all done by conservative forces, then solve the problem using conservation of mechanical energy. If any work is done by non-conservative forces, then solve using the work energy principle. And you can still use what you know about the potential energy for the force fields, the conservative forces. You can still put those in there because the work that they do is equal to the change in potential energy, or the negative change. All right. What homework problems would you like to see? Anybody? Yep. Yeah. Okay. Yeah. Nope. Yeah. So if right off the bat you say, okay, this object has a downward acceleration of a, that means this one has an upward acceleration of a. You can just put those right into Newton's second law in the start. Yep. Any homework questions? Number 14. Okay. Okay, so there's a mass hanging from the ceiling. We'll give that the mass capital M, and it's shot with a bullet with a mass little m. And when the bullet sticks into the mass follows a circular path. And now notice that the bullet and the mass swing together. That bullet is lodged inside of there. And it swings up to a height this is going to be part of a circle because the length of that string is going to stay the same the whole time. It swings up to a change in height of h. Okay. And we want to use that height that we can measure to figure out the speed of the bullet. Before there were high-speed videos and stuff, was the way bullet speeds were measured. This was actually a thing that people did to figure out how fast the bullet came out of the gun. Because measuring the height that this big mass swings is a lot easier to do than trying to measure the speed directly. All right, so what we're going to do, notice that the bullet hitting this thing is a collision. And since they stick together after the collision, it's inelastic, so we can do that problem. And so we're going to do an inelastic conservation of linear momentum problem to figure out the speed of the combined mass and bullet after this is lodged inside. And once we have that starting speed, we're going to figure out how high it swings and come up with a relationship between the height that it swings and the starting velocity of that bullet. Okay. Anyone have a question about the sort of roadmap of how to do this problem? So there's a collision. We know for the collision, we're going to use conservation of linear momentum. And after the collision, there's a swing, and that swing is going to work really well with conservation of mechanical energy. Okay, so the collision. You can think of this. I usually like to think of these from above. But either way, you have a mass hanging here with no velocity before the collision, and a bullet coming in. It has a mass of m, and it's coming in with a velocity of, I'll call it v bullet coming to the right. So conservation of linear momentum for an inelastic or a plastic, says the momentum of the bullet, if our, I'm going to use a coordinate system like this, the momentum of the bullet is little m times v bullet in the x direction, 0 in the y direction, plus the mass of the hanging mass, big M, and it's not moving before the collision. And then after the collision, the two things have the same velocity. So I'm going to call that, we can think of it as a single object with a mass of little m plus big M, and we can calculate the velocity. So I'm going to call this the mass of little m plus big M, and the velocity after I'll call v, I'll just call it Vx and Vy. We'll come up with a relationship between those and V bullet. Okay, so our X equation says M times V bullet is equal to the quantity M plus big M Vx. And that says that Vx is equal to the mass of the bullet divided by the sum of the two masses times V bullet. And the Y equation says 0 is equal to the quantity M plus big M times Vy. So Vy is equal to 0. Okay, so after the collision, so we can think of this as immediately after the collision, the velocity of the combined mass is an x component of m over the quantity m plus big M times V bullet, and then 0 for y. Okay, so the combined mass, if you look at that expression, after the collision, is the combined mass swinging faster or slower or the same than the bullet was coming into it? A lot, yeah, probably a lot slower, because that hanging mass is going to have a lot more mass than the bullet, you know? So if this is like a kilogram and this is like, I don't know how much a bullet weighs, a gram, 5 grams or something. This is a tiny fraction of the speed of the bullet, okay? And so now we've gone from something moving way too fast to get any good measurements with by eye and by hand to something moving at a speed where we can take measurements by hand. And now we're going to do the swing part. So now we're starting with an object like this, and bullet is lodged inside there. So this is the combined mass, and it's going to swing up to a position like this. And we know that the change in height of the center of mass of this system is h. Swinging problems, conservation of mechanical energy often works because that cable force is a non-conservative force. Okay, non-conservative forces often cause problems when you're using energy. But notice that this is a circular motion, and that cable force is always toward the center. It's a centripetal force. Okay, and remember, centripetal forces never do any work, no matter what the force is. So let's think of a free body diagram, and we'll see. It's just a representative instant. We'll think about the forces that are being applied. Okay, so there's a weight force that's equal to big M plus little m times G going down. And then there's a cable force, T, but this does no work. Yep, question? Oh. Right, it's perpendicular to the path at every instant. Yep. And so that means that the only force we have to worry about is gravity. And since we have an expression for the potential energy of gravity, we can use conservation of mechanical energy. Okay, so here's instant 1. Here's instant 2. Yes. Yeah, that's a good way to think of it. So if you think of it in terms of what work is with the integral, you can just think of it as mathematically, no force does work if it's always perpendicular to the path. Okay, but that's also a good way to think of it is if it's perpendicular to the velocity at every instant, then you know that it's only causing that perpendicular part of the acceleration, and that turns objects, it doesn't speed them up. You're right, that's totally related. Yep. Okay, so at instant 1, we have to figure out the potential energy due to gravitation. That's mgh. And remember, we get to choose the point that we call 0 height. So let's call this one h equals 0. And so at instant 1, there's no gravitational potential energy. And the kinetic energy is 1/2 times the mass of the system. That's the sum of the two masses. Times the speed squared. And the speed is this thing that we calculated. So that's little m squared over the quantity big M plus little m squared times v bullet squared. Any questions about that? I guess I'll do one cancellation here. So this is 1/2 times m squared over the quantity big M plus little m squared times V bullet squared. This, yes, that shouldn't be right. Thank you. Okay, and then at instant 2, the potential energy due to gravity is mg, well, m, I wrote it over here as m, but we're talking about the mass of the system. So this is little m plus big M. Same thing over here. Quantity little m plus big M times g times h. Because the height of this was given as h at the highest point. What's kinetic energy at the highest point? 0. Yep, it gets up, it's slowing down. Finally, it stops at the highest point, and so the kinetic energy there is 0. Now all we're doing is saying this and this and setting it equal to this and this. That's what conservation of mechanical energy does. So 0 plus 1/2 times little m squared over big M plus little m times V bullet squared is equal to quantity little m plus big M times GH. And now we're just solving for V bullet. So let's see. V bullet squared is equal to 2 times the quantity big M plus little m squared times GH divided by little m squared. And take the square root of that, and the speed, the muzzle velocity of the bullet is the square root of all this, which is the quantity m plus little m over little m times square root of 2gh. Any questions about that? So let's say the big M is 5 kilograms. Little m is, let's say, 1 gram. So 0.001 kilograms. Let's say that the height is 0.4 meters. Then the speed of the bullet coming out of the gun is 5.001 divided by 0.001 times the square root of 19.62 times 0.4. Can someone give me a number for that? $2.8? Okay, and then times. That's way too slow for an effective bullet. 14,009? Okay, that's not very realistic. That's way too fast, but I just made up those numbers, so meters per second. So yeah, so 29,000 miles per hour. That's too fast. So at a so it turns out that if you had a mass that big and a bullet that light, and you shot it into this mass, it wouldn't swing up that high. That's what we learned. But that's how the relationship works. Any questions about uh, any of the steps in that process? This thing is called a ballistic pendulum. I don't really know, but that's what I would imagine. It's pretty easy now to just shoot it and take a video of it and take the numeric derivative of your positions. What other questions would you like to see? Napoleon, did you have a question? 16? 16B? Oh, 13B, sorry. 13B. Okay, yes. Yeah, let's do all of 13. I think I have to do A to get B. Okay, so a skier with a mass of 50 kilograms skis across a flat section before reaching a 5-meter tall hill. Um, and for the skier to make it to the top of the hill, what's the slowest speed he can have on the flat? So we're trying to figure out his velocity here. Um, and then we want to do it 2 different ways. So what's the slowest he can travel on the flat? To reach the top if first there's no friction, and second, if friction removes 400 joules of energy from the skier. All right, well, first let's do sort of the common sense. If we're trying to find the slowest the skier can travel, the very slowest he can be going to make it to the top of the hill, then what's his speed going to be at the top of the hill? 0, yeah. If he's going any faster than that, he could have slowed down a little bit and still made it to the top. And if he stops before the top, then he didn't make it to the top. So our kinetic energy at this instant 2 at the top of the hill is going to be 0. Um, and we get to choose where our height is equal to 0. So might as well choose the bottom of the hill. But like always, it doesn't matter. You'd get the same answer no matter where you chose it. So first, let's say there's no friction. Let's think of a free body diagram of the skier. Forces acting are the weight. So that's 50 times 9.81, so 490.5. And a normal force. Those are the only forces. The normal doesn't do any work. It never does in rolling or sliding problems. And since gravity, we have a potential energy function for, since that's a force field, we can use conservation of mechanical energy. Right. Centripetal forces and normal forces in rolling and sliding are the two forces that will come up in almost all these problems, and they don't do any work. So instant one is anywhere on the flat. If there's no friction, the speed's the same the whole way along the flat. And then instant two is at the top of the hill. The gravitational potential energy is mg times the height of 0. That's what we chose as our 0 height. So there's no gravitational potential. And the speed, or the kinetic energy, is based on that speed that we're trying to find. That's equal to 1/2 times the mass of 50 kilograms times the speed squared that we're trying to find. And at the top of the hill, gravitational potential energy is 50 times 9.81 times the height, which is given as 5 meters. And so this is 2445.7, is that right? Or point 52, 2452.5, 52.5. These are all in joules, by the way. And then the kinetic energy is 1/2 times the mass times the speed squared, but at the top of the hill, the speed is 0. So the kinetic energy is 0. And now conservation of mechanical energy says 0 plus 25v squared is equal to 2452.5 plus 0. And so what do you get for v? 9.90 meters per second. Any questions about part A? Okay, so now we'll go on to part B. For part B, there's friction. And so since friction does work, we're going to use the general form. We're going to use the work energy principle. can't use the conservation of mechanical energy. So instead, we have to use the work energy principle. And the work energy principle says add up all the work done. That's equal to the change in the kinetic energy. And we can separate the total work done into the work done by gravity plus the work done by friction. Okay. And the work done by gravity is the negative change in gravitational potential energy. Okay, that's using that second relationship that we know for potential energy. So we can still just calculate the change in potential energy for gravity and get it into the work energy principle through this relationship. So I'm going to do the same thing again. I'm going to set it up, write a little table of instant 1 and instant 2, and these things are going to all come out the same. The gravitational potential energy at instant 1 is 0 because it's at our 0 height. The kinetic energy at instant 1 along the flat is 1/2 times 50 times the speed squared. At instant 2, the gravitational potential energy is 2452.5. And the kinetic energy is 0. Okay, so the change in gravitational potential energy is 2452.5 minus 0, so 2452.5 joules. So the work done by gravity is negative 24. Now it's the negative of that change in gravitational potential energy. That's negative 2452.5. And so now the work energy principle says the work done by gravity is negative 2452.5. Friction removes 400 joules. So is that, am I going to add or subtract 400 joules from the work? Subtract, because it's removed. And that's equal to the change in kinetic energy, which is 0, the final kinetic energy, minus 25v squared. And so 2852.5 is equal to 25v squared. And so what do you get for v? (10.68 meters per second). We want the positive one. So if as the skier goes up the hill, friction is acting, then to make it to the top of the hill, the skier has to start out going faster. Any questions about that transition between conservation of mechanical energy and the work energy principle? So you can use the potential energy in both of them, because in the work energy principle, the difference in potential energy is still the easiest way to calculate the work done by your conservative forces. You just need another way to calculate the work done by the non-conservative forces. And if you're lucky, like in this case, or anything I give you on a test or whatever, just the amount of work done by the non-conservative forces would be given to you as energy, and it's just a matter of getting it in the equation with the right signs and stuff. Okay, well, let's stop for today, and if you have questions about any of the homework problems, bring them tomorrow, and I'd be happy to spend as long as you want doing it. And if we get through that and you're done with questions, I guess we can go on to new stuff, but I'd be happy to just spend the time on this.